Hi, today I'm going to do a torque problem for you. So we're going to be dealing with a situation that involves both static equilibrium, where all the forces add up to zero, and also rotational equilibrium, where all the torques add up to zero. And this is kind of a real-life situation, a little bit of a fun one. The question: in order to paint the outside of your house, you buy an 8-meter aluminum extension ladder. The ladder has a mass of 12 kilograms and has rubber caps on the bottom of the legs. You put the base of the ladder on the sidewalk 2.8 meters from the side of your house. Can you safely climb all the way to the top of the ladder if the maximum coefficient of friction between the ladder and the ground is 0.78? We can assume that there's no friction between the ladder and the house. So this is an interesting one. We're just going to follow our normal process. So I've got a house and ground and a ladder. And I'm going to stand on the ladder somewhere. Okay, yeah, good enough. What do we know? We know that we put this 2.8 meters from the side of the house. The length of the ladder is 8 meters. And we know the mass of the ladder is 12 kilograms. And I'm going to remind you that it's often good right away to figure out what the weight of any object is, because we don't deal with masses, we deal with forces, which is the weight. So if you want to, you can, even in your knowns, your list of knowns, you can figure that out right away. So if we do that, 12 times 9.8 gives me 117.6, and that's a force now, newtons. All right, and what else did we know? The length was 8 meters. The maximum coefficient of friction was 0.78 between the ground and the ladder. And that's about it. Okay, doesn't feel like we have a lot. So here's our picture where we start. Here's our list of knowns. The next thing in our problem solving process is to figure out what our unknown variable is. Well, the question is, can you safely walk up the whole ladder without it slipping? That's not a variable. Normally we are asked for a variable. Find the tension, find the force. Here, we got to think about what to solve for. Can we climb safely up all the way to the top of the ladder? Well, one of the ways to figure that out would be to figure out how far up we can get based on the maximum friction that we're going to have between the ladder and the ground. So I think that would work for our variable. And if it doesn't, we'll try to find it another way. So let's see if we can figure out the distance that we can go up the ladder, the maximum distance that we can go up the ladder. If it's less than 8, it's not safe. If it's more than 8, it's totally safe. Okay, picture, knowns, unknown. Typically at this point we do the force diagram of our object of interest, but with torques we add one step to that. With the torques we are going to be doing an extended free body diagram or force diagram, where we not only put all the forces that are acting, but we also include where they act. Because torques, where a force acts, is at least as important as what force is acting. So an extended free body diagram. Okay, the object of interest, well, I'm going to guess it's the ladder. So let's do an extended free body diagram, or extended force diagram of the ladder. So here's my ladder. I'm going to draw it at an angle. And what forces act on it? Okay, well, gravity acts on the ladder. We know that the mass of the ladder is 12 kilograms. Gravity is going to be acting downward. And I'm going to put that right in the middle. I'm assuming the ladder is nice and uniform, so its center mass is going to be right in the middle of the ladder. I'm going to be acting on it, and the force that I exert downward on it is going to be equal to my weight if we're not accelerating. I'm just going to draw it somewhere up here. I don't know where that is. That's the mass of me times gravity. What else does the ladder interact with? So it's interacting with the ground, and it's interacting with the wall of the house. Let's look at this one to start with. We were told there was no friction on this surface, but something's got to be acting on the ladder to keep it from going whoop. So the wall of the house is exerting a normal force on the ladder. And normal forces are always perpendicular to the surface, so the wall is pushing perpendicularly on the ladder. We have a normal force of the wall pushing to the left. All right. And there's no friction there. I don't think anything else interacts with the wall. There's no other interaction between the wall and the ladder. So let's go see what we've got down here. Now we do have friction in this case. Same thing with the normal, but this is more normal, if you allow the pun. So this is more normal in terms of the normal force. We have the ground perpendicular. Our normal force from the ground is going to be straight up. And here we do have friction. So which way is friction going to be acting? Well, if this ladder were to slide, it would want to slide that way. So the base of the ladder wants to move that way. Friction opposes that motion. Friction is going to go this way. So we've got a friction force this way. Any other forces? Well, I don't think so. I don't see that the ladder is interacting with anything else. It interacts with the wall, the ground, with me, and the planet as a whole for gravity. One of the things I recommend doing is once you think you've finished off your force diagram, see if it makes sense. Can it be balanced with the forces? I have an upwards force here. I've got 2 downward forces. Yeah, that could be balanced. I have a rightward force here and a leftward force there. That also can be balanced. I think we're good. If you forgot the friction force, for example, and that wasn't there, and you looked at it and said, uh-oh, this thing's accelerating to the left. I must have missed a force. So keep in mind that just take a quick look at that force diagram to make sure it all makes sense. All right, now this looks a little different than the typical beam problems we've been doing. One of the things you can do if you don't like seeing all these angles is you can redraw it on the flat. So if you don't like seeing all those angles, just try redrawing it. So I'm going to put the ladder flat, rotate it. Oh boy. And now I got to figure out what direction these things are going. So the normal force on the wall is going to be going kind of like that. The mass of me, the weight of me, excuse me, is kind of going like that. The weight of the ladder itself, like that. Okay, so normal force there from the ground, and then the friction's got to be perpendicular to that. Okay, I think I got that right. These two were perpendicular. Yep, and the friction and the normal from the wall were the same, and then we've got the 2 weights in the same direction as the normal from the ground. Yeah, looks good. So for some people, seeing it this way makes more sense because you have fewer angles. A lot of people look at this and kind of freak out going, there's too many angles, I can't handle it. So just redraw it. All right, so we've got our extended force diagram. We're looking for the distance up the ladder. And here's where our equilibrium conditions come in. There are 3 equilibrium conditions. If something is not moving at all, we have 3 conditions. We have to have the net force in the x direction be 0. So all the forces horizontally have to balance. We have the net force in the y direction has to be 0. All the vertical forces have to be balanced. And then here's our third one, our new one. The net torque has to equal 0. So these two mean it's not accelerating left, right, or up, down. This one, this new one, this torque, means it's not rotating at all. So these are the 3 conditions for equilibrium. And we're going to see if we can use these to solve the problem. Okay, so let's see. How should we start? I often will start with the torques and then move to the forces if I need them. It doesn't matter what order you do them in. You will get 3 equations, and I don't care which one you start with. You can start with the forces, you can start with the torque. Doesn't matter. You'll come up with the same answer. I just tend to start with torques because if we're in this unit, we probably need to use torques to solve the problem. But hey, that's just me. So let's start with the torque. And again, we can use either one of these extended force diagrams. Which one? I'm just going to go with this one to start with. And if you need to do this one, that would be a good problem for you to work on your own to make sure you can make sense of it having drawn it this way. All right, so the net torque has to equal 0. We always have to pick a pivot point. So the pivot point, there's a couple good ways to pick it. You can pick it where the actual physical pivot would be. Where is this thing trying to rotate around? If you have a hinge in the problem, that's an obvious one. So you can also pick it based on well, okay, I think this is where it's going to be. You can just make a random guess. That's okay. One of the best ways to pick your pivot point is to pick a pivot where you get rid of unknown forces that you don't care about. So a pivot with a force acting right on it. So if a force acts at the pivot point, doesn't matter what direction the force is, if we're rotating around this point, no torque, it's not going to cause a rotation. So I am looking for the distance up the ladder. Holy smokes. Well, okay. Is there anything related to that? Okay, well this is me, okay? So I'm going to guess that this one's going to be important. So don't pick your pivot here. This is something we know, because we know mg for the ladder. So I'm going to say, let's try to keep this one. Then we have the normal force from the wall, the normal force from the ground, and the friction force. If I choose my pivot right here, I can get rid of 2 forces. I have 1, 2, 3, 4, 5 forces. And if I choose my pivot down at that bottom, I'm only going to have 3 torques because neither of these forces causes a torque. They're acting right at the pivot. So let's try that. I've chosen my pivot point right there. Now I'm going to do net torque equals 0. Net torque equals 0. So I'm going to take the torques, add them all up, set them equal to 0. I have 5 forces, but like I just said, only 3 of them cause torques. Okay, so these 2 don't cause torques. Let's see. What's the torque due to the weight of the ladder? Is it acting at a distance from the pivot? Yes. So my distance for here is going to be from the pivot to where the force acts. And now the torque is only caused by the perpendicular force, the perpendicular component of the force. So if I break this force up into a component perpendicular to the beam or the ladder and parallel to the ladder, only this one causes a torque. So I need to find out with this force, this weight, what is this component? Okay, I can do that, right? It's just like we've done a lot. We've been trying to figure out the components. So I've got mg going down, and I'm going to break it up, and I want to know what this one is. It's going to be mg sine theta, mg cosine theta, one of the 2. Unfortunately, we don't know the angle. So how do we solve this? Can we figure out one of these angles? We weren't given anything about angles here, so I don't have any angles in here. How do I solve this? Well, let's go back and look at my picture. I know this distance. I know this distance. This is making a triangle. I know 2 sides of the triangle. I can figure out the angle. So even though it's not given, I can figure it out. Well, what do we got? If the ladder is 8 meters long and it was 2.8 meters away, this is my angle. I have the adjacent and the hypotenuse. Adjacent and hypotenuse gives me cosine. So this angle, let's see if I can squeeze it in up here. This angle I can figure out by using the cosine function. But since I'm solving for an angle, you don't use sine, cosine, tangent. You use the inverse functions. Cosine of that angle is going to be adjacent over hypotenuse, 2.8 over 8.0. I want to solve for that angle. To get rid of the cosine, do inverse cosine on both sides. Inverse cosine of 2.8 over 8.0. All right, so then that'll give me the angle from the horizontal. And when we do that, we get 69.5 degrees. I'm just going to call that 70. So the angle from horizontal is about 70 degrees. Okay, great. Is that 70 degrees? Up here? Is that 70 degrees? Is neither of those 70? So we still haven't figured out our triangle here. Okay, we got to go back and look at the trigonometry. If I go back to this picture, okay, what do I have? This is 70 here. Okay, because that's what we figured out right here. Well, if this is 70, this up here must be 20. Okay, and I've got a right angle there. So if this is 20, whoop, that's 70 as well. It's getting a little small. This angle up top is also 70 degrees. Okay, now I can do it. We still haven't even gotten to the first term here. We've got a lot of steps here. This is adjacent to the angle. It's the cosine component. So the force causing the torque is going to be the mass of the ladder times gravity, the cosine component, cos 70. That's the force. The distance at which it acts from the pivot, well, I was assuming uniform, so half the length. So that's acting at 4 meters. And now we also have to remember, is it a positive torque or is it a negative torque? I'm going to put my finger here and say, which way would this force cause this thing to move? I'm pulling down on it. Okay, so this would make it rotate clockwise. Clockwise torques are negative. Okay, so there is the first term. Yay, one of the 3 is done. Okay, let's hope the others go faster. We did that one. Now we have to do this one, but it's not going to be as much work because, well, we have this exact same triangle. So I'm just doing the exact same thing. I know this top angle is 70. And we can say that the torque here, it's going to make it rotate the same one. So I'm just going to say mass of me times gravity times the cosine of 70. And it's acting at what distance? That's what I want to know. Okay, so that's what I want to know. This is the distance up the ladder. So I'm going to call this D. All right, so we've got the force, the perpendicular force and the distance. Perpendicular force and distance. Last one. Okay, so this one, it had better be a positive torque or these won't add up to 0. So this one, if I hold it here, it's going to make it rotate this way, counterclockwise. It's a counterclockwise positive torque. Oh man, I got to figure out my angles again. All right, so my distance is from here to here. I need the perpendicular part of the force. So I need this part right here. What's this component? That's the perpendicular piece. Okay, the hypotenuse is NW. I need to know an angle. Again, I need to know an angle. Okay, I'm going to look at the big triangle here. The big triangle. From horizontal up was 70. That means from horizontal to the same thing is also 70. So I can use some geometry and trig to figure that out. All right, so I think I got that. And when we figure this out, normal from the wall is here, and I need to go like that. And here's my 70 degrees. And so I want this part right here. It's opposite the 70 in this case. So you can't always assume it's going to be the same cosine or sine term. Here the force is the normal of the wall. We're doing the sine component. Sine of 70, and what distance does that act from the pivot? Well, that's the whole length of the ladder, 8 meters. Okay, so I had 5 forces. I have 3 torque terms. Add them up, they'd better equal 0. So let's figure out what we know. All right, MLG. Yes, I know the mass of the ladder. I know G. I know the angle. I know 4. I have to figure that out. This is the thing I'm looking for. Okay, that's got my unknown. Oh, shoot. I don't know this one either. I know that. I know that. I have 3 unknowns. I don't know my mass. I don't know the normal force due to the wall, and I'm looking for D. Still can't solve it. So I have 3 unknowns and 1 equation. I need more information. Well, okay, I said I don't know my mass, but actually I do. I know how much my mass is. So I'm going to say that I can figure out what this one is. Let's put that into my knowns. So this was the mass of the ladder. My mass, I'm going to squeeze it in here. The mass of Laura times gravity. So this is my weight. I'm just going to say 750. I think it's around there. So you could put your weight in, you could put standard weight. I'm not going to be picky about that one. This one says you. So put your weight in. So I'm going to say that my weight's 750. Okay, so now we can say that this is a known. Got it. All right, still need to figure out the normal force from the wall. I need to figure out how big this force is before I can solve for D. All right, so we just did torque net equals 0. We did one of the 3 equilibrium conditions. Now let's see what happens if we do the other two. So I'm going to say, figure out the forces. So this is going back, it's kind of like the whole force unit. We're going to say, what are all the up-down forces? How do they balance? What are all the left-right forces? How do they balance? And hopefully one of these two will help me figure out what the normal force of the wall is. So, I don't know, let's just start with the x direction. The net force in the x direction has got to add up to 0. The forces all have to be balanced left-right. How many forces do we have horizontally? Okay, and here's a subtle point. You don't have to keep your brain in this axis coordinate system. So we use this coordinate system along the object for torques. Now we're just dealing with the forces. We're no longer thinking about torques. You can go back to using your standard coordinate system. So in this case, clearly the standard coordinate system is going to make my life easier because I've got horizontal, horizontal, vertical, vertical, vertical. I'm just going to use a standard coordinate system. So how many horizontal forces do I have? 1, 2. Easy enough. Plus friction, it's going to the right. Negative normal force from the wall equals 0. So friction equals normal wall. Great! That's what I'm looking for. Woohoo! I don't know what my friction force is. Okay. So let's see here. Well, I do have an equation for friction. Maybe this will help us. Friction is the coefficient of friction times the normal force. And I see a problem here. I'm not going to be able to have this match up if this is that. Let's go back to our forces. If we have friction acting from the ground on the ladder, we want to use the normal force from the ground on the ladder. So this is NG. We're getting there? I don't know, maybe. We do know that. We need to know what NG is. Okay. We only have one possible equation left. Let's see if the vertical direction, the y direction, will help us. Again, everything's got to add up to 0. The vertical forces have to be balanced. Vertical, vertical, there's a vertical one. Downward, the mass of me times gravity. Downward, negative mass of the ladder times gravity. Upward, positive NG. Hey, I think we got this. If I solve this for NG, it's just going to be the two ways. Mass of me times gravity plus mass of the ladder times gravity. Okay, so NG is, okay, mass of me, what did I say, 750? Plus the mass of the ladder, I'm sorry, I should be careful, weight of the ladder, 117.6 newtons. So that's 800, oh shoot, 800, I can add, really, 867.6 newtons. Yes, I think I can do this. From here, okay, I can put NG into that, and that'll give me my normal of the wall, and from there, I can put that into here, and I can solve for my D, finally. So you can see that this is an enormous problem. There's a lot here. And this is harder than I'd probably give you, but it's a good way for you to see all the different steps and all the little subtleties in a torque problem. All right, let's give it a try. I know NG, so my normal force of the wall, if I can do that math real quick, the normal force of the wall is going to be mu 0.78 times 867.6. All right, I do that, and this is the weird one, 6767, I think? Yeah, 676.7 newtons. Okay, so there's the normal force of the wall. This was the normal force from the ground. Now I'm going to put this into here, and then I've got everything but D in this equation. Okay, at this point I need lots of room, so I'm going to get rid of, do I know? No, I'm not going to get rid of all of that yet. I can get rid of this. So at this point, it's up to you how you solve this big honkin' equation. A lot of people, if you prefer dealing with numbers, you can just put the numbers in at this step. And at this point, I actually often put the numbers in for myself too. Normally I like to solve it with variables, but these are complex. There's a lot here. Okay, we ready? So the first term, I'm going to have a negative MLG, 117.6 times the cosine of 70 times 4. Okay, so that's the first one. Negative mass of me times gravity, 750 times the cosine of 70 times d, my unknown. And then here we've got a positive 676.7 times the sine of 70 times 8. Those all have to add up to 0. Okay, I'm going to go through the last couple steps of the ladder problem, which I had a mistake on. I mixed up my sines and cosines, which is a really common mistake for people to do, and even teachers do it. So there you go. The equation we had was negative 117.6 times the cosine of 70 times 4, half the length. That's the first torque. The second torque was 750 times the cosine of 70 times my unknown distance d. And then the third torque was 696.7 times the sine of 70 times the whole length of the ladder, which was 8 meters. Those all have to add up to 0. Okay, so when you do those calculations, oh, it doesn't want to let me get bigger. Okay, when I did them just now, I get negative 160.9 minus 256.5d plus 5087 has to equal 0. So then you should get something like 4926 equals 257d. And if you do that, d equals about 19 meters, which means that we can walk 19 meters up the ladder before it starts to slip. And since the ladder is only 8 meters long, we're all good. So that's the correct math for the end of the ladder problem. I hope this makes sense, and if you have any questions about it, as usual, you are always welcome to talk to me about it. Now, just out of curiosity, are there ways that we could make it safer? What could I do so that I could get all the way up the 8 meters of the ladder? Well, heavier ladder, that would probably do it. I guess the best thing to do would be to increase the size of the friction force, which means increasing this. So we want to make those legs even stickier against the ground. The rubber caps are going to do a really good job. This is a pretty big coefficient of friction, but we'd want to increase that. Or I guess I could go on a diet, decrease my weight. But yeah, those would be what I'd have to do in order to make this safe. Because right now, you can only get 2 meters up the 8 before it's going to fall. We've answered the question. It's reasonable and thought through everything. I think we're done. Good job.